recall, just on the simple level, if I have parallel plate capacitors, if I have an electric field going that way, that the change in the potential is equal to negative E dot delta X. If the electric field is constant, if it's not constant, negative integral of E dx s, whatever letter you happen to be using. Or generalizing E dot ds, if that's the other formula. So that's equal to negative change in magnetic flux with respect to time. Maxwell's equations. This Gauss's law of electricity. Gauss's law of magnetism. Ampere's law. With Maxwell's correction. And then what's usually called Faraday's law, but I think in fairness, Faraday-Lentz's law.
Was there a fight over credit for that formula?
I have no idea if there was a debate there. I think Lentz was Russian and Faraday was English. And so I suspect that there was probably a geographic difference about what people called it.
Don't they usually name things like hundreds of years after they've died?
Not necessarily, not in some of these cases.
Okay.
What about makes it Maxwell's equation?
All right, so why Maxwell's equations? All right, first off, Maxwell did not call them Maxwell's equations. That came afterwards. And so the key thing here is what Maxwell did with it. And I'm going to do a conceptual approach to what Maxwell did. I have a charge here, some charge Q that I'm going to move over to here. So imagine that you are at some point P here, and you're looking at that electric field. So the electric field is going in that direction, and then by the time the charge gets over here, the electric field is going that way. My electric field changes. Because my electric field changed, then my E dot ds is not zero, and so I've got to change my magnetic flux. That change in my electric field causes a change in my magnetic flux, which actually causes a change in the magnetic field. If I have a change in the magnetic field, well, I don't have, out here I don't have any charges moving, so the current that I have is the displacement current. I have got this. So that change in the let's try that one again. Change in the electric field creates a change in the electric flux. I don't know if I said it properly last time, but I definitely wrote it wrong. A change in the electric flux creates a magnetic field. From this, if I have a change in my electric flux, I create a magnetic field. So if that charge suddenly moved back, so my charge is moving back and forth in some sort of cosine or sine form, then I've got a change in the change in electric field, which creates a change in the change of that, which creates a change in my magnetic field, which creates an electric field, based upon what we have down here. I guess think of the intermediate step, creates a change in the magnetic flux, which creates an electric field. If I have this thing S going back and forth consistently, then I'm going to have a change here, and change there, change there, change there, change there. and that creates a change in my electric flux. And I get this cycle going. I get this, some sort of wave that is propagated out, created based upon this changes in electric field and magnetic field, and this is known as an electromagnetic wave.
Oh.
If it's a wave, you should be able to come up with a formula for the speed, and I won't do the derivation right now, I will do the derivation at some point. But it turns out that the speed of the electromagnetic wave, which Maxwell did primarily from these two equations here, there's another form of this derivation, which is a little bit slicker, but it does require everyone to have had Calc 3. But the speed of the wave ends up being 1 over the square root of u sub naught times epsilon sub naught. Well, we know some values here. If that's the case, we get 1 over square root of 4 pi times 10 to the negative 7 decimal meters per ampere times epsilon sub naught, which is 8.85 times 10 to the negative 12 coulomb squared per Newton meter squared. Square root of all that. Someone be kind enough to calculate that. Now recognize all he's done is find the speed of an electromagnetic wave. What's about to come out, presumably, is going to be why they honored him with calling these Maxwell's equations.
8.99 times 10 to the 16.
You forgot to do the square root.
Sorry. Uh,
863380.
993380.
299863380.
10 to the 8th.
2998630. Seems like there should be another
3380.
3380. Units?
Volts?
What do we just find?
Meters per second.
Yeah. Found a speed.
The velocity.
So Maxwell comes upon this number here, realizes that is really, really close to the speed of light. Draws the conclusion, he doesn't state it absolutely, he says it does give some evidence that light is an electromagnetic wave. And he is absolutely right.
What a guy.
Yeah. This is the point in which we now are going, the electric fields and magnetic fields really do exist. This was more than just a mathematical convenience, but we now have some evidence.
So you like changed the game?
Yeah.
No.
However, physicists looked at this, thought this was a great breakthrough, but there are a group of them who said there's a mistake. I don't know what the mistake is, but there's a mistake in that equation. There's got to be something wrong. That's my question to you. What is wrong with that equation?
There's different types of waves.
Well, these are all electromagnetic waves. You're talking about different frequencies?
Yeah, there's different frequencies.
Well, the speed should still be the same, these, according to this. That's not the issue that was causing problems.
The direction.
No, that's not the problem, it's just the speed, so there'd be no direction there.
Is this like a relativity problem?
What do you mean?
Well, if light doesn't travel instantly, then that means that you're seeing everything in the past.
Yeah, why is that wrong? Why is that a problem?
Because then time can change depending on where you are. That's
Uh,
concerning.
You did a couple of leaps there,
That is
you,
So
you ended up, you ended up in some correct areas, but your
So-
leap that you made missed.
So like one person standing at the board compared to you
Right.
will see you quicker
Yes.
than me seeing you.
Yeah, that's not a problem.
But then, now let's say that I saw a really good explanation, but I don't remember how to explain the explanation
All right,
myself.
let's simplify it. How fast are you moving right now?
Not at all.
Same speed as you.
What did you say?
The same speed as you.
Are you really?
No. We're going 0 miles per.
I mean, our frame of reference is like we're not moving at all, but then like as we get wider and wider, then we're going faster and faster.
So how fast an object moves, I mean, from Hector's point of view, I believe Hector was talking from his own point of view, he's not moving at all. But in this equation, its speed depends upon the observer. Where is that in this equation?
I was.
It's not there.
It's not there.
So this is mid-1870s, early mid-1870s. Next 30 years, some physicists were trying to figure out why is it not showing up. They went through all of Maxwell's work, they didn't find a problem. They still, Lorentz, probably the main guy, there's a group of equations called the Lorentz equations, was trying to come up with an explanation for why we're not seeing it here. There's definitely something that odd, there's a mistake here, but he was trying to go through of why we can't see it. Einstein comes along.
It had to be Einstein.
Einstein comes, so this is 30 years later, Einstein comes along and says, let's assume that he is correct. That the speed of light is the same regardless of the reference frame. What does that mean? Well, you came up with a thought experiment. We're going to call this the lab frame. In other words, you're on the lab, you're watching this thing happening. I've got a box that is moving to the right at some speed v. I have a mirror up here. The box is going to emit some light from upwards, but it's got a sideways component to it, so the light's going to come up here, and then it's going to be caught again over here. So from the box's point of view, the light's traveling that far. Or actually, sorry, reword that. From the lab's point of view, the light travels that far. Now let's look at it from the box point of view. The box's point of view, the light goes up and comes back. This distance from here to here, why don't we just say is L? That would be the same for both of them. Speed, distance over time. What does it tell you about, what is this distance here?
Sorry, would you clarify what you pointed to?
The light's traveling from here to here to here. What is the distance that the light travels?
Isn't it the same length?
Pardon? I heard the length at the end.
Oh, I just said, isn't that the same length as the up and down? It just looks
No.
like it's different?
Oh, no,
What-
no, it's not.
what's
This length right here is just 2L.
Sorry, what's the how far does the box travel in the lab frame?
Sorry, what was your question again?
How far does the box travel in the lab frame?
Let's say it travels some distance VT.
Okay.
So it travels VTL? Wait, no.
If the halfway point, which is where that point would be, this would be half of VT. This is length L, so what would be the hypotenuse here?
L squared plus 1/4 V squared T squared, or VT squared? Or square root of that?
Yes, there you go.
Sorry.
So the square root of L squared plus 1/2 V squared T squared. So according to this, the speed that the light's traveling is 2 times the square root of L squared plus 1/2 VT squared over time, and this is 2L over time. V, oops, I got two different V's here, sorry. This is the speed of light, which I'll just call C. Are those two equal to each other?
No. Or at least they should have been.
All right, no, they're not. As long as this V right here is not zero, they will not be equal.
Oh, but they're both the speed of light.
So if the speed of light is the same, what else has to be true? Because the distances aren't the same, but the speeds are the same.
Time has to be different.
Yes. We'll call this the lab time, and we'll call this the Fox time. Those times are not the same.
Oh. Oh. Oh.
So, as you move, well, actually, let's drop back for a second. All right, so I got the two different times there. I've got, so I have 2L. L is over time for the box is equal to 2 times the square root L squared plus 1/2 V squared, let's go ahead and square it. 1/4 V squared T squared. That is for the lab over T lab. If Maxwell has not made a mistake, if the speed of light is the same, then those should be equal to each other. So it's both speeds of light. Let's get rid of the 2's. Let's square both sides. So I get L squared over TV squared is equal to L squared plus 1/4 V squared TL squared over TL squared. Let's get rid of fractions by cross. Let's see, do I want to cross multiply yet? Not yet. I need to get TLs together though. All right, so I will cross multiply. So I get L squared TL squared equals L squared TV squared plus 1/4 V squared TL squared TV squared. I know from that equation up there that 2L over TV is equal to the speed of light. So L would be 1/2 C TV. Did I make a mistake?
No, it's just length is equal to 1/2 the speed of light times the time being. Okay.
Yeah, because C is equal to 2L over TV.
Okay.
All right, we'll make that substitution. I am taking a slightly longer way than I meant to, but we're here. So I have TV squared, TL squared is equal to, plug that in, so I got 1/4 C squared TV squared plus 1/4 V squared TL squared TV squared. I have TV squared in each of these, so I can just get rid of that. And now I'm going to get the TLs on one side because I want TL all by itself. I'm going to bring this over. Oh, I got 1/4 everywhere too, so let's get rid of the 1/4. So I have C squared TL squared minus V squared TL squared is equal to C squared TV squared. Factor the TL out. TL squared times C squared minus V squared is equal to this. And so now I can come up with a relationship. It's not going to be in the standard form, but I will get there shortly enough. So the lab time squared is equal to C squared TV squared over C squared minus V squared. I'm gonna multiply top and bottom because I know where I want the final result to look like. 1 over c squared times 1 over c squared. And I'm left with tb squared on top, and on the bottom, 1 minus v squared over c squared. Square root of both sides, and I get TL is equal to TB over the square root of 1 minus v squared over c squared. This is the relationship between the two different times. Now recognize that in the box frame, the box is not moving at all. That is the rest frame. So the box frame in this case, box frame is the rest frame. Or is often called the proper frame. So we'll generalize the equation that t is equal to the proper time over 1 minus v squared over c squared. So if you are traveling at 10% of the speed of light, so you're driving to school and you're traveling 30 million meters a second, 0.1 times the speed of light, then the time that will be measured by someone who is, say, at school timing you. Let's say that they know when you left, they know when you get here, and they say it took you 2 minutes to make that trip. How much time has passed for you in the car going at 10% the speed of light? Well, that will be TP over the square root of 1 minus 0.1 squared. So the proper time, you in the car, it's going to be 2 minutes times the square root of 0.99, which is
.9949.
times 2.
1.98.
1.9899.
Minutes. So how many seconds is that?
59.39 seconds. Well, plus 60.
So 100,
Oh,
119.
Yeah, is that 119.4?
Yeah.
all right.
19, sorry. I just did the 0.98 and then calculated the 1 minute 60. Yeah.
So rounding off to 19.4.